Welcome everybody to our forum on U.S. and global nuclear power. Our speaker is a distinguished SAIS graduate, Dan Lipman, who is the Vice President at the Nuclear Energy Institute for supplier, new reactors, and international programs. A very broad portfolio. The Nuclear Energy Institute is the trade association of America's nuclear utilities. Dan will say a little more about what all they do. But as his title implies, he's heavily involved in representing U.S. companies and promoting their interests of sales abroad, nuclear exports, trade legislation, things of that kind. But I think just more recently, has added this other part of this title, which means that he's also supervising new reactor technology, and we'll be saying something about that, including, I suppose, small modular reactors, things of that kind. Dan joined the NEI in 2014, became vice president in 2015, and has been there since. Before that, he had a 30-year career with Westinghouse Electric Corporation, starting with at the lower levels, including working on various plant sites and construction, later customer relations. But he has done many things at different times. In the period 2005-2009, he served as senior vice president for nuclear power plants for Westinghouse. And as I recall, during that time, he spent at least a couple of years in China and played a pivotal role in negotiating contracts between Westinghouse and China for the AP1000 reactor, which is the most advanced reactor at that time, and which has since been constructed and is actually adjusting this period coming online. Maybe Dan will say a few words about that. He, I think, has worked both in U.S. and a couple of other international sites. And I'm not going to go on further about his background. What I will observe that it's kind of remarkable and a good lesson for SAIS students to look at someone who's did not have a technical background, but got interested in energy at SAIS actually before we had an energy program, and interested in nuclear issues, and went on to make such a fabulous career that he's done. I do recall he may have stepped out and picked up a few courses in nuclear engineering at some point, but his career has been remarkably successful, and we welcome you back.
Thank you. Okay, so a couple of questions. How many of you are students in here? All right. How many of you went to the Bologna Center? Okay, so I'm also a Bologna Center guy. I was Dr. Cole's research assistant. He made the mistake of giving me an office and a salary. It was like my first real job besides washing dishes for a while. From there, I went to the International Atomic Energy Agency, and that was my first jacket and tie job, right? And stayed in nuclear power ever since. I came back here, got my master's degree, and immediately went into, before I joined Westinghouse, a small company here in town. I worked a couple of years, and it was a consulting firm, and SAIS prepares you for that kind of work. We do research and writing and those kinds of things and analytical work, and I really hated that. So I then got a job for working for Westinghouse in Korea, and I worked at a construction site in Korea just a couple of years after graduating from here, and never really did anything else other than work in the nuclear power industry. So if it ain't got neutrons, I don't know how it works. I've spent a whole life in this industry. Anybody here anti-nuclear? It's okay, you can raise your hand. Yes, a couple smiles, okay, you can raise your hand high, it's okay. So I'm not going to try and convince you one way or the other, but I'll just tell you what's going on out there. I hope by the time you leave here, you'll have a good taste for what the current dynamics of the industry are, both inside the United States and outside the United States. For me, Professor Cole talked about different assignments I had. I told you I worked in Korea, but I also worked for 4 years in China. I was the president of Westinghouse Electric Asia. I had, when I became the senior vice president of nuclear power plants for Westinghouse from 2005 to 2009, I had a number of global operations in Europe, here in the United States, a couple locations including manufacturing of nuclear power plant components that are still made in the United States, and also for everything we did in Korea, Japan, and China. So, but there were times I worked at construction sites. I told you I worked at a construction site in South Korea. I also worked at one in the Philippines. I worked at one in Texas. It's kind of a foreign country. And in Georgia, not the country, but the state. And at times like those, it seemed like the closest thing to my SAIS degree was my subscription to Foreign Affairs magazine. Okay, I wasn't doing international work, but I volunteered for every one of those assignments. So you might say, well, why'd you do that? You know, and I did that because I wanted to be closer to the technology. I wanted to understand how it worked. I wanted to get a sense for who are the companies in the industry, how do people operate the technology, what are the issues surrounding it. And I don't care whether you decide to go into nuclear energy or some other energy technology, the one thing I would advise you to do is take assignments, take jobs that bring you closer to the technology, and especially the people that run it, people that lead it, so you get a sense. I don't care whether it's solar energy or gas or whatever you like. Each industry has its own, each energy industry has its own dynamics, good and bad, its own technology issues, its own R&D issues, funding issues, customer issues, regulatory issues, you name it. But it's, you know, one thing you do get from SAIS, I thought, and I still do think, is a pretty good perspective on how to analyze industry dynamics, how to interact across cultures, and not just foreign cultures, but organizational cultures. Okay, that's important too. And so we bring, with our SAIS background, I think, a pretty good understanding of cross-cutting, how to analyze and how to work within cross-cutting issues. So I give you that as background because, I mean, it was a long time before I felt that I was really utilizing my SAIS background. But I did, you know, and I would say for at least the past 20 years, you know, I'm glad I graduated from here. I'm not saying I wasn't glad I graduated from here. I'm just saying that for the first long period of my career, I did a lot of things that were very unrelated to SAIS. Now, you have the energy program now, which Professor Cole said didn't exist when I was here. We cobbled together different courses to kind of make a specialty in energy. Now you have, I've looked at the curriculum, and I'm really proud to see you really do a deep dive into subject matters that, you know, I had to learn on my own and continue to learn. But you have the opportunity to formally study this stuff under great professors that help you think through the current issues. So I tell you all that as a way of just, I've been gone from SAIS a long time, okay, and I'm just telling you that as you look forward into a career, value what you learn here, but what you're learning is how to learn, because industry dynamics have changed tremendously since I went into my first nuclear power plant a couple of years after I graduated from here. So I'm going to show you that. Stop me if you have any questions, and we'll get started. I asked Professor Cole, because most of my work has been international, as you might expect. I said, well, I'll focus on international stuff, right? And he said, Yeah, but cover what's going on in the United States. So that means you get the world, and so we're going to talk about home and abroad, kind of a pithy title, right? Okay. Okay, so some quick statistics regarding the nuclear energy industry. I think the most important things are, it's not a huge industry, but it's not a trivial industry. There's about 500,000 people that work in nuclear energy in the United States, or for U.S. companies outside the United States. The other thing is the economic impact of the industry. A lot of contribution to GDP, a lot of contribution in taxes, but the most important things are up top here. First of all, you've got nuclear energy contributing about 60% of carbon-free generation. And for those of you who are coming at this from the environmental end, you've seen some of the very latest reports that indicate if you're going to meet a 2 degrees Celsius reduction in temperature, or even, as the latest study says, I think 1.5, you need nuclear power plants to continue to operate, and you likely need to build more in order to achieve that. And those are some of the statistics with respect to how the U.S. operating fleet contributes with respect to carbon emissions, SOx, and NOx. So we have our role, and I think one of the big changes is, and I'm going to go through this in some depth, in the United States, how is that valued? Okay? So at NEI, we've put together a strategic framework. So how do we approach the nuclear industry? Okay, you've got preserve, sustain, innovate, and thrive. Preserve and sustain have to do with the operating fleet here in the United States. How do we keep it from further reductions in operating plants? And you probably know a number of plants have shut down or announced they're going to shut down. Sustain, how do we reduce the regulatory burden? How do we improve the economics? And I'll talk about that. And then innovation really gets, as Professor Cole said, to the advanced technology aspects of our industry. New reactor designs, reactors under construction, how do we build them more cheaply, more effectively? And then finally, thrive, which is global competition. And that's something that probably interests a lot of you in terms of who's doing what outside the United States and where are the key competitions outside the United States. So I'm going to talk about all 4 of these frameworks. And I talked about dynamics. Here really are a set of dynamics. Let's spend a little time on them. First of all, in this country at least, electricity demand has been flat, and in some parts of the United States has not even recovered to the pre-financial crisis 2008 levels. Other parts of the United States have indeed recovered. The Gulf Coast, for example, is actually slightly growing, both because of population dynamics and also because of the oil markets, which have put a lot of petroleum product in the refining and petrochemical complex. Natural gas technologies, Mark, I heard you talking earlier about fracking and what that means. I think clearly since 2008 or so, the recovery of natural gas is really one of the hallmarks of the U.S. economy right now. I think it's no exaggeration to say it has been a complete and total game changer with respect to the U.S. energy markets, and we'll talk about that. And then we have, because of state and federal policy, we've seen dramatic growth in solar and wind deployments in the United States, and the cost curve for deployment of those technologies continues to be reduced. They're becoming much more competitive in certain parts of the United States. But one of the most important things here is electricity markets really don't recognize the value of nuclear. So if you go back to the other slide, the first slide, and I'll make this presentation available, you can have this, but on that upper left-hand part of and I'll go back to this, up here, carbon emissions, SOx and NOx. except for recently, nuclear power plants are not compensated at all for any contribution to reduction of carbon or SOx or NOx reductions at all. Nor are they compensated for the contributions to the local tax base or anything like that. Nor are they compensated for energy diversity or energy security. Zero. Basically zero. Now there are some states that have taken action on this, but basically we have no price on carbon. And I know you're probably talking about that in certain of your coursework. When you go outside the United States, particularly to Europe, you see carbon trading regimes, and it's a much different approach to carbon, okay? But right now in the United States, there's essentially no price on carbon. There's a social cost of carbon that's been derived. That's not the same as a market price. And that's resulted in closures. So let's take a look at this, okay? The first two on the left, Crystal River and San Onofre. Those are reactors that closed. Crystal River's in Florida, San Onofre is in California. Those closed because of mechanical reasons. In the case of San Onofre, they received replacement equipment from Japan, from Mitsubishi, that was defective, that didn't work. They were steam generators that came from Kobe, and when they started them up, they vibrated to failure. And so they had an option. Who's they? The utility in Southern California, in Southern California, they could replace those again, or they could shut down. They opted to shut down. In the case of Crystal River, they had cracking in the containment vessel due to something known as sort of stress in the tendons of the containment building. It's a structural issue that they faced. Again, they decided to shut down. But all of the rest, Kewanee, Vermont Yankee, Fort Calhoun, Oyster Creek, and all of these that have announced their shutdown have shut down because they can't make money, okay? Now, I can tell you Kewanee, which is one of the older plants in the United States, was one of the, generated electricity at one of the cheapest prices per kilowatt hour in the United States and had a tremendously favorable safety record. And it simply could not make money. In other words, the price of natural gas had driven down in the capacity markets the price of electricity, and that utility could not compete. And so if you're on the board of directors of a utility company, all right, not a state-owned enterprise like in Russia or China or Korea or France, if you're running plants for profit, you're not going to keep open a facility that doesn't make money, okay? And so you have a number of plants that have said, we're shutting down unless or until there's legislation that changes the game. Now I'm going to talk about that, but let's look. This is in Pennsylvania, this is in Massachusetts, this is in Ohio, this is in Nebraska. Dwayne Arnold's in Nebraska, I think? Iowa. Indian Point, New York, Beaver Valley 1 and 2, Pennsylvania, Perry, Ohio, Palisades, Michigan, and Diablo Canyon 1 and 2 is in California. Now, in the case of California, they're going to run this until the end of life, but then they're not going to renew their license, okay? So this is a phenomenon that's across the United States with one thing in common. About half the states in the United States are regulated electricity markets, and what that means is that there's a public service commission that's generally elected by the people of that state that sets electricity rates. About half the states in the United States are what's known as free market, merchant market states. The other half are not. The other half, that public service commission sets the electricity prices. In the free market states, it's the free market that sets it, which generally means the price of natural gas. And natural gas is what, $2 or so now, maybe a little less, or what is it?
It's been fluctuating between like around 2 or 3 for the past while.
For the past while, so-
Yeah, the past actually quite a couple years.
Right, and so it ain't gonna change much from there, unless you tell me something different. Everything I've seen, right, everything I've seen is that's about the price, marginal price of natural, it now fluctuates with time of the year, okay? But nonetheless, that's the price against which these plants have to compete. And if you're not getting value for your carbon contribution, if you're not getting value for contribution to energy diversity or security or anything like that, you're just competing against natural gas, period, all right? Okay, so one thing to keep in mind, nuclear safety is regulated at the federal level, from right here in Washington, from White Flint, from the U.S. Nuclear Regulatory Commission. Nuclear economics, on the other hand, are regulated state by state, generally speaking, state by state, okay? So that's important to keep in mind, because what it means is that a lot of the political activity related to preserving and sustaining the operating fleet and building new ones is a process that has a great deal of political power in individual states. All right, that's important to keep in mind. So the color coding here basically are, let's look at the yellow first, plants preserved. So Illinois, New Jersey, Connecticut, and New York within the last couple of years have passed legislation which is favorable to nuclear, meaning it gives either a price on carbon or it gives a credit for non-emitting sources, or it gives some sort of incentive to those technologies that can contribute to greenhouse gas emissions reduction, okay? In the, whatever color this is, what color is that? Pinkish, I guess. What you have are states that currently have or will have in their upcoming legislative sessions bills that they're going to address that could do the same thing. So my home state, Pennsylvania, Ohio, and Minnesota are going to be important with respect to the nuclear plants in that state in terms of picking up legislation. And if you go back to the other slide where I had on the right-hand column, a lot of those plants are in Ohio and Pennsylvania. Also, here's the other thing. Ohio and Pennsylvania also generate a lot of electricity from what? From what source? Coal, all right? So you shut down nuclear, I can tell you Pennsylvania, like I said, it's my home state, about 36% of electricity comes from nuclear, all right? You shut that down, all right, it's gotta come from somewhere else. And it's gonna come from either gas or it's gonna come from coal. And notwithstanding the tremendous contributions to demand side management, which we've been able to do in this country, in being more energy efficient and using less electricity and so forth, you will have a change in profile on greenhouse gas emissions. Those Pennsylvania plants that are going to be shut down will wipe out 100% of the carbon-free generation that solar and wind currently produce. Right? It's just not good. All right? Irrespective of how you feel about nuclear, it's just not good. That clean air technologies of any sort are sort of boxed out of the market. There's a couple ballot initiatives. I guess after tomorrow we may know something in Michigan and Nevada and Arizona on a clean energy standard. So some of you have heard renewable portfolio standard, RPS, you've heard that expression. There's also a clean energy standard, and sometimes nuclear is included in a clean energy standard, sometimes it is purposely excluded. I might make note that up until last November, so a year ago, nuclear was not considered a clean energy development mechanism globally. But now and that was sort of embodied in the Clean Energy Ministerial, that ministers of energy from all around the world would get together and discuss. For the first time, nuclear was included. Now, why was that? That's because, and I'm not going to get all the countries, but basically Japan, Canada, and the United States got together and said, look, we all have to recognize the value of nuclear energy. It's got to be included in the debate when we as energy ministers talk about clean air and how we realize the benefits of the Paris Treaty. So that's a big, that's a big change. You also have a couple of states, Utah, Tennessee, Missouri, and the state of Washington have small modular reactor legislation. So these are economic incentives passed by those houses of representatives or senates and the governors to encourage small reactor development. Now we'll talk about small reactors later on in the presentation, but it's interesting that, the message here is that there's a lot going on in states. And I can tell you one change I noticed at NEI, 3 years ago we weren't doing a lot in states. Now we have people in all of these states. We're all over, especially these. We were particularly involved in New York and Illinois because survival of the fleet is very, very important to us, all right? And I'll talk a little bit about the interplay between operating fleet and global nuclear deployment a little later in the presentation. But you need to keep this map in mind. And I think, if I'm not mistaken, the dots are currently operating nuclear units. And so I'll say something else. You'll notice that the southeast and up here are sort of the centers of nuclear energy generation. Well, why is that? Well, first of all, coal is in the north and the west primarily, okay? Coal transportation is an important economic component of how economic coal is or is not. And so, down here, you're far from coal fields. You're kind of far from natural gas, although that's changing, right? With new ways of recovering gas. And same here. It doesn't mean new nuclear plants won't be built elsewhere. In fact, there are. In Idaho, we're looking at a small modular reactor project. I'll talk about that. We have construction going on in Georgia, as a matter of fact. But I think the point is that's where the nuclear plants are. Okay, these were nuclear plants saved by those legislative measures that I was talking about. More electricity generation than all U.S. utility solar in 2017. 60 million metric tons of CO2 avoided. Bottom line is, whether you like nuclear or not, it's making a contribution to our clean air, and it's very, very significant. These are all plants that, based on the legislation I talked about in New York and Illinois and New Jersey and Connecticut, these are all the plants that were saved. Okay, and let's look at jobs also. The economic impact of these plants is very, very significant. Usually you have about anywhere from 800 to 1,100 people working on these sites, plus all the businesses that go on around it. Okay, so one of the initiatives we have is called Delivering the Nuclear Promise. Basically, it's, if I look at my nuclear plant, I want revenue to go up. That's from those, from either from carbon, a price on carbon, or a level playing field with other renewables. But I also have a cost side, okay? And nuclear plant costs have varied quite a bit. One of the things that we've seen is, beginning in 2001, shortly after 9/11, we began to see a creep up in nuclear plant operating costs. All right, so here I'm just looking inside the room. What's it cost me to put outside a kilowatt of electricity? And we were seeing an increase in those costs. Well, why is that? Well, for starters, after 9/11, there were some very significant security investments that were made, physical security investments from seaborne, air, and land attack. Second thing is, there has been a lot of investment in these nuclear plants to basically increase their megawatt output, which enable them to generate more electricity out of the plant. And that's based on new technologies, efficiencies, changes in turbine blading, and so forth. So basically it's getting more juice, if you will, out of the technology, out of the plant. So we started to see, therefore, an increase in cost, and so we began to look at, all right, well, what's driving that? You know, what do we need to do in order to get costs out of the plants? And so delivering the nuclear promise, otherwise known as DNP, is something that's been, I guess, for about 2 years in place. We've come out with efficiency bulletins. These are chief nuclear officers that get together in rooms just like this and sort out what can we do together to help us operate more effectively and more efficiently. And it can be pretty mundane. It might have to do with how you process workers in and out of your plant site. It may have to do how I do engineering changes, you know, when I make modifications to the plant. Even within a nuclear fleet owned by one company, it's not unusual to have different sites using different processes. I mean, it's just clearly not efficient, all right? So what we've seen is almost 20% drop since 2012 in cost at the fleet level for nuclear. Now, one of the things I will say, one of the things that hasn't dropped is efficiency of nuclear plants. For about 15 years, the fleet operates at over 90, and the last stats we have, I think, from last year are about 93% capacity factor. That's very, very high, all right, compared to coal, compared to any other generation source. So the whole idea behind nuclear plants is you bring them up and you let them run 24/7, 365. That's the whole basis behind the current fleet. Now, new technologies are a lot more flexible, and we'll talk about that and their relationship with renewables. But basically, the operating fleet is all about operating their plants for significant periods of time. Okay, I'm going to talk about innovation here. The whole idea on innovation is really to talk to you about what new technologies are being considered and that are being invested in right now. You recognize this guy, right?
Yes.
What's this guy doing? Well, he happens to be a tremendously pro nuclear advocate, all right? And he owns one of his many enterprises is one called TerraPower. And they have over here, it's called the traveling wave reactor. It's big. It's not a small reactor. It's fairly large size, all right? And they're out in Bellevue, Washington, and what I'm going to give you is kind of a quick tour over these advanced reactor technologies. But here's what I want to say strategically about them. They fall into different families. Some are small modular reactors that are based on light water, just like the current fleet. Some use liquid sodium or molten chlorides or other forms of salts. Some use high temperatures, all right, which brings with it some very, very interesting applications, have nothing to do with electricity generation, because you create not only electricity but also high quality steam. And that steam can be used in other industrial processes, all right? They also operate with different kinds of fuel. They have very different safety parameters. And there's something like, and I'm not exaggerating, 4 dozen different reactor concepts out there right now in the United States. A lot of them are funded by private equity, either West Coast equity or Wall Street equity. And some of them are gonna die, okay? It's a Darwinian process. Not every, all these concepts start as paper reactors, all right? And you have to do a lot of testing because you're gonna have to get them licensed. Remember, nuclear safety is done at the federal level, and so all of these concepts will eventually, if they're gonna be commercially applied, licensed by either the U.S. Nuclear Regulatory Commission if they're gonna be built in the United States, or by some other, what's known as competent regulator, all right? Okay, so this is a conceptual drawing. It's not one in particular, but the first thing you wanna visualize is, for a lot of these smaller technologies, at least 50 to 70% of the reactor is underground, okay? Which brings with it a lot of different benefits, okay? It means that so a lot of security concerns are really gone. You know, you're not worried about air attack or other kinds of assaults. The safety case for these plants is significantly statistically improved, and therefore you can shrink the emergency planning zone around these plants. And in fact, just last week, the U.S. Nuclear Regulatory Commission approved the changes in emergency planning zone, all right? And that can be very, very significant. That means the staffing that you need is significantly reduced, and one of the drivers of cost is personnel, okay?
Sorry, excuse me.
Yeah.
When have they been changed to? They were 10 and 15 miles, right?
Well, it depends.
Depends
It's
on
now
the-
like 2 miles.
Oh, okay.
It's a very significant change. But it depends on the design. It's not
Of course.
2 miles for everything. You go with your design to the NRC and they say, this is what you're looking at. So the small modular reactor that the company NuScale, which is up in Oregon and is looking to build in the state of Idaho, they're looking at about a 2 mile, we call it EPZ. And what do? They look at what's known as the source term, which is the amount of radiation. You assume a terrible accident. You must assume a terrible accident. What's the maximum amount of radiological release you can have? And then you size your EPZ based on that, okay?
Can I ask you a question?
Yeah, of course you can.
As far as, not in my backyard, so does that come up a lot?
Yeah, great question. And actually, I don't have a slide on it, so I'll talk to it. So, when you look at public acceptance in the United States, what you see is a little less than 60% public acceptance of nuclear in the United States. When you look at places that have nuclear plants, it's more like 85%, which is unsurprising, right? Because it's there, it's been a neighbor, your next door neighbor works there, your kids do internships there. I mean, whatever it might be, you're used to having it. And so new plants are very likely to be built at existing nuclear plant sites. And I'm going to show you one where it's built at an existing nuclear site. Or the other thing we're seeing is a lot of these smaller technologies are being built as coal plants retire. Because the footprint of the new generation of nuclear plants is so significantly smaller compared to a larger plant, they can very often go on exactly the same site where a coal plant is. And the folks who live in that backyard generally a lot happier having the coal plant shut down and a non-emitting source come in. Thirdly, a lot of these small plants are so small, they will serve, and this is particularly true in Canada, where if you go up to the Northern Territories, they burn so many communities which are quite small, 3,000 people or under, sometimes in the hundreds, they burn diesel, which is arguably the first or second most expensive source of energy to burn. I mean, imagine running a truck, a bunch of trucks, 24 hours on diesel to generate your electricity, number one. Number two, they are beginning to impact the air quality in those small communities, particularly up in northern Canada. So here you have communities asking, hey, I want a small reactor, and I want it dedicated to my community exclusively, okay? And the other backyard issue is some of these smaller, brand new technologies are going to be sited at or near national laboratories. So it'll be on federal land. So I mentioned a project in Idaho. They'll be on the grounds of the Idaho National Laboratory. Idaho National Laboratory is federal land. It's already got a whole bunch of nuclear facilities on it, and so that's typically not a problem. But great question. Thank you for asking that. By the way, let's look at the non-support. We're not going to be building any new nuclear reactors in California. Okay, it's an anti-nuclear state. However, the new law they have allows for nuclear electricity to be imported. All right, they're happy to take nuclear kilowatt from Arizona or from other states. Actually, Idaho has an interconnect with California, and I met with the CEO of that. It's actually a Utah utility that'll build in Idaho. He'll sell part of that power in California. They're okay with that. They just don't want it in the state of California. Similarly, in New England, not going to be any nuclear plants in New England. It's not a pro-nuclear environment, okay? And they don't like pipelines, so there won't be gas pipelines going in there either. So you always have to take into account public acceptance. Okay, so this is one of the big plants. This isn't a micro plant. I told you I worked at several plant sites. This was one of them. Except I'm old enough to have worked at Vogtle 1 and 2, okay? Which is a traditional reactor. This here is an AP1000, all right? We sold this in April of 2008, and it's a pretty revolutionary design. It's modular construction. So what you can see is you would normally see a big containment building. This is different. This is built in modules, and as each one is done, concrete is brought in. If you could see into here, and you can, this brown component here is the steam generator. That sits in what are structural modules. Modules are prefabricated components that are made in factories, and they're shipped to the site and installed directly. Now, why is that important? Because, so it's November, all right? Pretty soon it's going to get cold here. If you're a construction worker and you're working in November, December, January, and February, you think your productivity goes up, or you think it goes down? It goes down, and it goes down pretty severely. And if you're working in a place like Georgia in June, July, August, and September, similarly, your productivity goes down. So having factory-built modules is an innovation that smart guys, and I don't mean me, I mean really smart guys, when they put this design together back in the 90s, you know, I did this contract, and I know this technology, but the point is, there's about 360 modules, and they go from the size of building, several thousand tons, to about the size of this table, okay, of equipment. It's done in factories, done under controlled conditions, workers are indoors, and then it's barge or rail or truck shipped to the site. And so, if you could see in here, I think we have another, this is not an interior picture of it, is it? No, sorry. Okay. Anyway, you would see modules, and then you would see equipment come in, and it sits, they plump it right down into the modules. The advanced technologies, the one I was talking about a minute ago, they're almost 100% factory done. The only thing that gets done in the field is the big hole. All right, there's a big hole whenever you are at a nuclear plant. Okay, but this is underway. This picture is pretty recent, probably within the last month. This is outside of Augusta.
Can I ask you a question?
Yes, you can.
What about the development of those modules? Are those all done domestically, or is that something that's an international protocol, or do we share, or do you have proprietary rights over certain kind of modules?
Right, another good question. So the answer is a little bit of everything. The modules for these plants are made in the USA. The largest components come from Korea, Italy, Japan, are probably the three countries that have significant, and South Korea, have significant content. So very few components, but the biggest ones do come from outside the United States. Why is that? Because we don't make big vessels in this country anymore. We have no place, and I mean no place, that makes ultra-large forgings. All right? Ultra-large forgings are those above 30,000 tons or so. Okay? And those are made in very few countries. India, Japan, Korea. Okay? So the biggest components are all done outside the United States. But there are thousands of line items. So for example, this stuff, all the concrete, the steel, the electrical equipment, that crane, that's all made in the USA. All right? And so keep that in mind, because when we talk about international, you'll see another driver here for that impacts international competition. So that's a great question. But this component came from South Korea. So did the reactor vessel where the fuel sits. The fuel's made in the United States. It's made in South Carolina. This steel here is actually made in the United States, and the forming and bending of it, it's not that thick. It's very thin steel, is also done here in the United States. When you go to this project, all right, this is in China. So the first AP1000s are now in commercial operation in China. We signed that contract in 2007, I think. I think we signed it in 2007. Construction started several years later. They built a lot of their own modules under Westinghouse direction. They imported some big components, some big forgings from South Korea, but the Chinese industry makes its own. They also imported a lot of American equipment for that plant. So Sanmen 1, which is the one closest to us, is now in commercial operation. So if you were to look, for those of you with anybody here been to a nuclear plant before? Okay, so what you'd notice, this is a really small, this containment structure is relatively small. This is standard. You go to any nuclear plant, that turbine building, is a 1,200 megawatt turbine building. That's pretty typical of anywhere you'd go. What's amazing about AP1000 is the small nuclear footprint that it has. And these smart guys, the fellows and women that I was talking about before, they developed something called AP600. It didn't pass the economic test, so we needed to get more megawatts out of it. They built up instead of going out this way. So they kept the same footprint for environmental, water use, and so forth, but they went up in elevation. So pretty impressive, okay? So this is an operation. The next site is Haiyang. You have a picture of that, right? That should be the next one. I want to say something else about these. They kind of look the same, right? And if we go back, right, you can see how that is going to look like that. That's called standardization. Standardization is very important because when you look at the current fleet in the United States, there's not a lot of standardization. Yes, there's the same generic technology, pressurized water technology, boiling water technology from Westinghouse and GE respectively, but the plant designs can be quite different. They're essentially custom-made designs. And we felt that standardization was the key to good economic performance in building new nuclear plants. So when you looked at countries like France, when you looked at countries like South Korea, they had standard designs that they replicated over and over again. And they've done a really good job in building them, okay? Even though the technology is older, they've been able to build them very effectively, very efficiently. And so and now I can say, when I and my staff were putting together this design, one of the things we said is we want this standard. So the question was, well, how standard do you want it, Dan? And I said, I want the carpeting and the door handles to be the same everywhere in the world. Now, that was an exaggeration, right? But I mean, it's not, I did say that. And the carpeting and the door handles are the same. But what we really mean is this part, the nuclear part. That nuclear plant the nuclear part of the plant has got to be standard wherever you go. Why? Because it's safer. If you have a regulatory issue, you know it. The nuclear equipment is the same. Doesn't have to be built by the same person, but it's got to be to the same, or company, but it's got to be to the same design, the same specification, the same licensing basis. And most importantly, the operators, when you bring an operator from one country to another, or from one plant site to another, they know exactly what they're looking at. The maintenance issues are the same. The operating issues are the same. The safety issues are the same. Very, very important. And new for the United States, not new in other countries. This part of the plant is basically the same wherever you go in the world, but not entirely. Not entirely. But this is where the carpeting and the door handles doesn't exactly hold true. There are differences in here, in this building. But all the nuclear stuff, the mechanical auxiliary building in here, that's a standard design, whether it's in China or whether it's in the US, or if it's built outside. Yes, ma'am?
Does that include like standardized training for the?
Yeah, absolutely, absolutely. So the control room, which is very interesting, the current fleet, if you're under 40 years old and I brought you into a nuclear plant, you looked at the control room, you would say, this is like a Rube Goldberg, sort of thing. But that was it. It was analog, and they have switches and buttons and things like that. Not AP1000. AP1000 are TV screens. Actually, screens not unlike what you see on these shades. Operators look, they see the parameters, and it was a control room that was designed by operators for operators. What we did was we got US utility operators, and we said, come up here meaning Pittsburgh, and tell us what's in your ideal control room. And they did, all right? A lot of them were younger, and they said, I want to use a mouse. I want touch screens. I want procedures not to go to a book and read a procedure. I want it on the screen when I click on it. Okay, now you would say, well, of course, right? But that wasn't the case in the nuclear industry. I wasn't trained. I'm a certified reactor operator, but I'm not licensed. I can't operate a plant, but that's not the way I was trained. Okay, but this generation of operators says this is the way I want it, and it is standard everywhere you go in the world. Obviously, if you go to China, it's in Chinese, but the man-machine interface is in the language of the home country. But all the engineering simulations, the control room, the buttons you push, the enunciators, that's all the same. Did you have a question?
Yes, so this slide here doesn't look anything like that plan into the future you showed us earlier.
It's bigger,
Okay,
much bigger.
But you said that one would be largely underground. This
Right.
one seems to be going out.
This one, that's right. This is a Generation 3 plant that's being built, more modern than the ones that are operating in the fleet. All right. The ones I talked about, and we'll talk about, are Generation 4. They're much smaller. This is 1,200 megawatts. those that are underground are much smaller than that. They're in the hundreds or even tens of megawatts, okay? So, a different size. This one here, these here are for baseload electricity. This one here will run in China and in Georgia. It'll run 24/7, 365. The other ones can, but they're also made to be a lot more flexible and to take advantage if there are solar and wind components nearby, which are great during certain weather and great during certain times of day. Nuclear plant will back off and then come back on, say, in the evening. All right. So there are different designs for slightly different applications. This is a full baseload plant. Okay, this is a big plant. So just so you know, Sanmen is kind of in the greater Shanghai area. Haiyang is in the northeast in Shandong province. Thank you.
Can you give us, can I have one quick question? Can you give us a basic primer on placement? Do these go near water? What type of climate is perfect for this? And what's the output?
Okay, so the output of this generation of design is about 1,000 megawatts. About 1,000 megawatts. GE has a design that's more. The French have a design that's a lot more, but you're in at least 1,000 megawatts or more. And they're bigger, to the previous question, they're bigger plants. Water. Every nuclear plant needs water, okay? What's interesting about AP 1000, it needs a lot less water. And in fact, it's certified for river applications. So these Chinese plants are right on the seacoast, both in Shandong province and in Zhejiang province, all right? They're right on the seacoast. The one in Georgia is on river, all right? And therefore, because it's river, you'll see those cooling towers. So where is that picture of me? It's got these cooling towers. It has nothing to do with nuclear. The picture of me, this one. Well, in the flyer. If you look at the flyer with a picture of me, yeah, this one here. See this? That has nothing to do with nuclear, okay? That could be a coal plant, could be a gas plant. Everybody likes to see that. I don't know why, but these are not there, but they are in the one in Georgia. So if you're near a river or other water source, inland water source, you use cooling towers. If not, you use sea cooling. And then you said weather conditions. I mean, look, you've got nuclear power plants in the Arizona desert. You've got nuclear power plants in the United Arab Emirates, kind of aggressive temperature environment. You have nuclear plants in Minnesota. Have nuclear plants, what else is cold? What, Finland? Kind of cold, right? I'm guessing. Then I'd say, cold, right? It's cold in Finland?
Trust me, it's cold.
Okay. All right, so they operate in different environments. And by the way, it can matter. Your accident condition can change. You know, certain of the very, very technical analyses can change. Hurricanes, you know, if you're sited, so I worked in Texas, I told you for a while. It was south and east of Houston. I had to evacuate with my family, and they were little kids at the time, 2 times because of hurricanes, all right? And those plants operated during hurricanes. We've had some major storms in the southeast in the last 3 or 4 years. You all know that. Sometimes the plants continue to operate through the hurricanes. Sometimes they shut down, and they usually shut down because as power lines go down, you've got 1 million watts of electricity with nowhere to go. All right, so you shut down. All right, but those are some of the weather conditions that could conceivably impact you. Okay, so when we talk about the advanced reactors, one of the things has to do with local power. All right, people want plants to serve their community, but what we're finding is folks in Silicon Valley, sort of specifically, looking at dedicated power plants like Google. All right, they're talking to NEI and others. Why? Because they use a lot of electricity, right? Lots and lots and lots of electricity. And so having a dedicated power plant is one of the market drivers for these smaller technologies. Speaking of smaller technologies, there's an organization called SMR Start, and these are companies. It's a combination of buyers and sellers of the small modular reactor technology. There's Canadian plant. There are Canadian utilities, American utilities. This is the utility out in Utah that I said was interested in building. And these folks are interested in what are the generic issues that they have to address in order to get these smaller technologies built. I want to talk a little bit about legislation. And they have these, there's NECA, NELA, and NEMA. Mark, this is going to be a test for you. You should know this, right? So, but NECA, NEMA, and NELA. NECA is the law of the land. Right? This one is the only one of the three that's an actual public law now. And basically, those are the features there. And this is important. It's a way of encouraging advanced reactor development because, believe it or not, we do not have a versatile test reactor here in the United States. If you want to go test fast neutrons, you got to get it tested in Russia. In Russia. So U.S. companies today go to Russia and they buy testing services from the Russians. That's okay, unless maybe your relationship isn't too good, okay? Then it becomes a little more problematic, all right? So NECA is an important new development where this was spearheaded largely by Department of Energy with a lot of support from our organization, NEI, to help with that law. We also have the National Defense Authorization Act known as NDAA. The important part of NDAA is it pays for U.S. soldiers and sailors and Marines, but there's also often, it's a bit like a Christmas tree. You know, people hang different asks that they have, and one of them had to do with microreactors, and it's going to encourage a pilot program at defense establishments. All right, so the Department of Defense has a desire to be off the grid, right? For lots of different reasons, either at military bases or even forward deployments. A very sad statistic, I think, sad statistic, is something like half the casualties in Iraq, half the U.S. casualties in Iraq were incurred bringing diesel or other fuel sources to electric power plants to keep the lights on in Iraqi cities. And there's a lot of work being done on certain types of plants, including nuclear units that can be forward deployed to do that. And that doesn't mean build a nuclear plant and leave it in a battle zone. That's not the idea. But the idea is to have transportable nuclear technology that can be utilized. CFIUS stands for Committee on Foreign Investment in the United States. It's got to do with money that comes from China, Russia, Saudi Arabia, other countries to invest in U.S. technology. NDAA puts restrictions on that. This too is the law of the land. But there's also several others. I mentioned NELA. All of these, if I'm not mistaken, the big ones here, NELA and NEMA, have passed through the Senate. Probably not going to get through Congress this session, but they'll be addressed. And what's great about them is they're bipartisan legislation to encourage various aspects of nuclear development, including such things as power purchase agreements. So one of the things I mentioned about nuclear plants closing down because they couldn't make money, well, if you establish a power purchase agreement, I presume you may teach something like this in your course, Professor, you know, having a floor under electricity prices is a really important economic issue if you're going to be generating electricity. It would enable you to take a power purchase agreement and monetize it by going to Wall Street or going to the banking community and saying, hey, I've got an agreement for the U.S. government to buy electricity or for these consumers to buy electricity, and can I borrow money based on this order? Very, very important. So I would encourage you to have a look at the different features of the different legislation, since it's important. Last part, probably your favorite, Thrive. This has to do with global competition. Okay, so I want to make a very important point. If you remember nothing from this, remember this. There is a very, and I'm telling you from 40 years in this industry, never before has there been as strong a linkage between success in the international market and success in the U.S. domestic market. You will not be successful outside the United States unless you have a thriving U.S. nuclear industry. And the U.S. industry will not thrive unless there's an opportunity for global exports. Take that to the bank, okay? It is very common now for U.S. companies, U.S. nuclear companies, and I don't mean big ones, but even small ones, to have more than 50% of its revenue coming from outside of the United States now. Okay? In Westinghouse, we crossed that threshold in about 2002. That was before China was sold. Okay? So there's a lot of nuclear commerce outside the United States. Will wanted me to sort of talk about what countries are engaged outside the United States. And this is sort of impossible to read, right? But you're going to get these slides. And what you're going to find is that almost all of these have, the blue are power plants in operation. And they're all over the globe. And then the green, and I'm going to show you the green in more detail, are under construction. And the red are those that are shutting down. They're shutting down for different reasons outside the United States, not economic reasons. They're shutting down either because of public acceptance and a desire to stay away from nuclear energy, like the Energiewende in Germany, like in Switzerland, like in Italy, or they're shutting down because they're very old, like in the United Kingdom. There were reactors built in the 1950s that are just too old to operate, and they're shutting down, and they're slowly being replaced. But this gives you a sense of where the action is. And let's take a look at where the big action is. France is a big operator, China is a big operator and a big builder, Canada a big operator, United Kingdom a big operator and going to build more. And of course, the biggest fleet is in the United States, but that red part of this histogram is starting to encroach that way. Let's take a look at construction, okay? This is a very interesting slide. China, India, and Russia dominate in terms of the number of reactors that they're building. So I told you we're building 2 in Georgia. So do the math, 54 minus 2. That tells you that more than 50 reactors are being built outside the United States. That's a lot of activity, but we're building very, very little in the United States. And if you go back to my sort of triangle of the U.S. and the outside the U.S. and the R&D necessary, that's very important in terms of nuclear leadership. These are some of the major markets. I'm going to talk about some other ones here in a minute, but these are places where they're currently, and when I say under construction, I mean earth is getting moved, concrete is being poured, workers are doing things, okay? And they're building all different kinds of designs. Russian designs, some French designs, or their own designs. Okay. This is worth spending a little time on. This is sort of a comparison between the US, Russia, and China. And on the left-hand side, I put, all right, what are some of the factors that go into global leadership? Okay. Operations, all right? Strong in the United States, but we're losing ground because we're shutting some plants down. Russia and China are growing. New building, very little in the US, lots of build outside in Russia and in China. R&D, there's some R&D going on, but not like we see in Russia and in China. And then innovation, we have a tremendously strong innovative culture here in the United States, but it goes hand to mouth. It's very hard to get, it's very hard for US developers to get money to carry on. And then the policies are mixed or they're supportive. I would tell you in my experience, and I've worked through a number of different US administrations, every administration is always favorable on exporting plants. Everybody likes to export nuclear power plants from the United States because it creates tens of thousands of jobs. Building them inside the United States and making the investments through the Department of Energy and R&D, maybe not so much. That changes from administration to administration. But this is a slide that's worthwhile talking about in class, in my opinion. Okay, so here's some of the biggest, here, in my opinion, these are the top 4 markets, okay? Top 4 markets: China, they're both a builder, but they're also a customer. Saudi Arabia, at least until 3 weeks ago, I would have said was a pretty good opportunity. I've been to Saudi Arabia maybe 6 times over the last 7 months on commercial missions with Mr. Perry when he went over to talk about nuclear technology. I was there last month for a few days. Spent a lot of time in Saudi Arabia. Now, this is a country that is no longer interested in burning its own fossil fuels for electricity. It feels it needs to diversify. It also needs small nuclear in order to furnish steam and for industrial applications in its petrochemical complex. Mexico definitely already operates nuclear units, looking at building 2 more. And then Poland, which is a very, very, very coal-dependent economy. And oh, by the way, they have natural gas. Where do you think it comes from? Right. They're not so thrilled with that, okay? So for them, nuclear energy is an important issue of energy diversification. And so when you look at the reasons why countries build nuclear, here's another thing to take away from here. There are many, many different reasons. China wants to build nuclear because it wants to export nuclear power plants. And it's active in the export market. China has a very robust nuclear industry. Saudi Arabia, they want it for a different reason. They want it because they're an entirely fossil fuel dependent economy. Mexico, they have a price on carbon. Mexico has liberalized their electricity market, worth looking at, and they consider and have considered nuclear a clean technology. And then Poland, I mentioned, it's an energy security issue. So the point is, not everybody wants to export nuclear power plants like China. Saudi's not going to export nuclear power plants. Mexico's not going to export, but they're going to make stuff themselves. Modules. You asked a question about modules. Poland, if you look at the northern part of Poland, the Gdansk, the shipyards, they can make modules. They have that capacity. They make ships. That's a very, very electromechanical intensive economy. So every country will operate plants, but they'll make portions of it themselves.
So you don't think UK would be on it?
That's a good question, Mark. So these are competitive markets, okay? The UK, you'll remember, were kind of real estate deals. I mean, each developer bid on and bought real estate where existing nuclear sites were, or sites that were gonna have nuclear plants, and they self-developed them. So the one you're thinking of is probably Horizon. That was bought by Hitachi, and they're developing their own site. These here are competitive markets, okay? In the case of the UK, the developers bought land, bought nuclear sites, and they're developing. The French at Hinkley Point and Bradwell, they're developing their own sites with their own technology. That's not the case here. But you raise a good point. I mean, I guess you could put the UK here. There's gonna be new build in the UK, and the UK has very, very favorable climate, economic climate for nuclear. They've signed on, I mean, think about this. They were an early signer of the Kyoto and now the Paris Agreement. They used to have, there's no more coal in the UK, against the law. They've run out of gas in the North Sea. They import some from Russia. And their nuclear units, which I told you they built in the 1950s, are aging out. They are a poster child for new nuclear, okay? And so you're right, they are an important market. I would say just not a competitive one. We're almost done here. So one of the things that's changing, we're seeing a lot more interest, particularly in this administration, to consider nuclear energy in its national security context. And this summer, there was a letter written to Secretary Perry by dozens of national security experts linking what I talked about earlier: strong domestic program to global competitiveness and global leadership. In other words, basically saying to Mr. Perry, who do you want to be the global leader in nuclear? Do you want the United States to be the global leader in nuclear, or do you want some other country to be the global leader in nuclear? And so that's what this letter says. You can get it on our website, and we can make it available to you. But it basically takes a swing at China and Russia, but not from the economic development point, not from the jobs creation point of view, and you won't find the word carbon in here, all right? It's all about national security. So look, one of the big things out there is financing. How do you build these? Where do you get the money? If you looked at those countries, besides China, that were up there, Poland, Mexico, Saudi Arabia, they all need financing. And we don't even have an export-import bank here in the United States that's authorized to loan money. I mean, for heaven's sake, Denmark has an export-import bank for furniture, okay? We don't have an export-import bank that can operate. We've got to have an export-import bank. They have not confirmed a new chair and new directors. Number one. Number two, it's not just export-import bank. There are also banking syndicates and other tools. There are regional development banks that are anti-nuclear, and you can't borrow money from them, okay? So more here, but I'm running out of time. The other big issue is export controls. This is basically the amount of time it takes to get an export control license from the US government. It takes more than a year. 10 years ago, it took about 150 days. 20 years ago, it took about 3 months, okay? And you're competing against the likes of Russia and China, and you need to go down to the Forrestal building and apply for your export license. It takes more than a year to get it. Now here's the good news. In the case of Saudi Arabia, after the IAEA General Conference of 2017, when the Saudis said, okay, we'd like American companies to bid, the Department of Energy approved an export license in like 3 months, all right? And that's as it should be. They have to do a non-proliferation review. They have the intelligence community that has to opine on what does it mean to have nuclear exports to a particular country, and what are the proliferation risks. That's appropriate. But don't tell me it takes 450 days to do it. And this is more export control stuff. I spent a lot of time on this. This, by the way, this is a good thing for SAIS people to work on. And this is the kind of thing that goes to the heart of interagency review. Mark, you've studied this, have you not? Export, Part 810?
Well, we do that, yeah.
Yeah.
I think it's an issue for Congress.
Right, so this would be an issue for Congress. And in fact, one of the pieces of legislation that I referred to in that list, I said there was NECA and NELA. Well, there was one in there that was very specific to nuclear export licenses. Congress has said, it's taken too long. You're eroding American competitiveness, okay? Okay, this basically indicates that for Russia and China, nuclear is part of their foreign policy, okay? Now, during the Bush administration, specifically related to India, civil nuclear trade was a linchpin of the Bush foreign policy to India. But when I look at pictures of, for example, Vladimir Putin, and he goes to a country, I always see people I recognize in those pictures, okay? Because they're guys who used to do what I did, and they're part of Rosetta. And he takes his nuclear people, his fighter jet people, his radar people, his mining people, you know? I mean, it's part of statecraft, all right? We don't do that. And I'm not suggesting we have to, But I am suggesting that's what we're up against, and that's what's important here. So we want American officials, and we encourage American officials to talk about nuclear energy and to encourage with countries that we want to have a relationship in nuclear energy to talk about it. Why? Because when you sell a nuclear plant like the kinds I showed you in the picture, it's about a 100-year relationship. By the time you sign a contract, design it, build it, and then operate it for 60 to 80 years, a century has gone by. So it's a very important economic relationship that helps to stabilize what we think stabilizes the bilateral relationship. We have lots of friends out there that are pro-nuclear, but they're pro-nuclear for different reasons. I mentioned national security, but there are climate change people. There's a lot more folks. You know, Greenpeace, I couldn't believe this. They took down their anti-nuclear webpage like 2 weeks ago. I was stunned. I was just stunned. Okay? We have friends out there who are interested, like Bill Gates, in innovation and technology leadership. The labor unions, very, very pro-nuclear. You know, when I go down to the IBEW or the United Association that do the electrical and mechanical craft workers, very, very pro-nuclear. But not for the same reason. You know, when I go to the unions, they don't talk to me about carbon. They talk to me about jobs. When I go to environmental organizations, that's their big thing. They don't care about jobs. They care about is the air. They care about the environment. So the point of this slide is there are many constituencies that support nuclear. What we find we have to do is mobilize them in different ways, because what's important to the national security people isn't important to the jobs people. Okay? Conclusion. We need more money. We need more money. The fleet needs more money. Trade promotion, so you can get money. Export controls, be efficient, get technology properly reviewed, but get it done quicker. And then loan money, okay? So people say, oh, it's just about the money. Yeah, it's about the money, okay? But the point is, this is about technology and creation of jobs and American leadership, okay? So that concludes my presentation. I'm open to questions, and I know I went through this kind of fast, but I hope your takeaway is you understand a little bit more about the interplay and the relationship between the U.S. domestic fleet and what's going on outside the United States, and how there's no other way to characterize it, smash-mouth international competition that there is for nuclear exports. I mean, everywhere I go, I mean, I travel about 100 days a year outside the United States, and I see the Russians, I see the Chinese, I see the Koreans competing with U.S. companies. And notice I said those countries, because they're all state-owned enterprises. The Americans are companies, and we're competing against state-owned enterprises. I see that all the time. So it is a very competitive landscape out there, but that's okay. You know, we like to compete. You know, we think we can win. We have won, but it is very difficult out there. So I hope that gives you a sense of some of the dynamics. Thank you for listening.
We have a little reception in a few minutes to where we can talk more informally, but let's suggest we take 3 or 4 questions now. Yeah.
So you just go back to your money.
Could you introduce yourself?
I'm sorry, Jeremiah Yaksavich, Energy Information Administration. You have your wish list of money here. What, from your opinion, is the biggest bang for your buck to preserve nuclear? Of your choices of other things you're going for.
Okay, so you said preserve nuclear. There is no question that if there were a price on carbon, the dynamics would change. If there were carbon legislation here in the United States that monetized, you know, non-emitting technologies, not just nuclear, but solar and wind and so forth, I think that would go a long way to preservation of the current fleet. In terms of outside the United States, I think having good lending practices, Let me tell you something. Russia and China are not part of the OECD. They do not follow OECD guidelines. So we'll never be able to match Russia and China financing packages. But having an operational Ex-Im bank would be very important. And certain agencies in the U.S. executive branch that have a restriction on nuclear lending, like OPIC and the Trade Development Administration, having policy change. It's not in law, it's in policy. If those change, that would be good. And then the last money thing I would say is budget, a budget for the funding of these new technologies that are so promising and that no one's even close to the U.S. on. These Generation 4 technologies, that schematic in a sense. So that would be my wish list.
Tell to Mark Holt, Congressional Research Service, what would you see as the process for funding and selecting demonstration plants for new technologies?
Yeah. So the big worry people have are picking winners. You hear this a lot. Well, they want to pick winners. I think an assessment of market potential, regulatory success, and economic competitiveness are probably the screens, Mark, that I would use in assessing technologies. And then I'd make recommendations. And if you had lenders that followed those criteria, you'd have this Darwinian process that I referred to earlier accelerated. Now, here's the issue. This micro reactor, what are micro reactors? Under 10 megawatts. They're going to serve very small areas. They'll serve a military base or a community. Those need to be nurtured, but you have to have a process like the one I just described in order to make choices. If it's a state-owned enterprise system, like in China, well, China's big, so they can afford a couple different technologies, but even the Koreans, they've picked one or two technologies and they focus on it. And I don't think we can afford to have 40 different technologies. I mean, it just doesn't make sense to me. So a sensible application of various criteria, and I mentioned a few of them, Mark, that's probably what I would recommend. You got a question?
Yeah, so I've been going to SMRs. Sorry. I'm Annalisa Gaggenheimer. I'm a student here in the ERE program.
Are you any good? You good student?
That's the professor.
Okay. I wasn't, that's why I'm asking.
So I've been following the UAMP steel INL pretty closely, and it seems like there's a lot riding on that for SMRs to be successful in the U.S. So what do you see as kind of the critical steps or kind of the critical factors that occur for that to really shape?
Okay, so I want to do a definition here of SMRs so we're clear. Small modular reactors get used interchangeably with a lot of different technologies. In this case, when we talk about small modular reactors, we're talking about light water, not any other coolant, okay? And so they're very similar to the big reactors I showed you on the AP1000. They're very, very similar. So getting that, in my view, the critical success factors are you've got to get through the US NRC faster than they are. They're currently on schedule, but it's a 42 or 40, maybe 46-month schedule. That's just too long to license a plant, particularly one that's safer than other designs. I mean, I want regulators to take advantage of these inherent safety features if they're well tested, and truncate the licensing process. So from the development side is that. Second thing, it gets to the gentleman's point about money and where could we spend money. Everybody know what the Valley of Death is? Okay. So getting over the valley of, and I've had to go through the valley of death with AP 1000. It is a really unpleasant journey. Just have to tell you. Like, I had black hair when I started it, and I don't now. It is very, very difficult. It is very difficult. And having a secure funding source, and it's a public-private partnership. I'm not saying, hey, federal government pays for it. That's inappropriate. But to have a funding source that is shared in a public-private partnership in whatever percentage, whether it's 50-50, 70-30, 30, I'm not making a policy recommendation here, but to get through the valley of death, because the biggest concerns I have with my own design, AP 1000, was I never got to final design in enough time, and that caused project delays. You've got to have a design that's done before you deploy it to the field. So the second major piece after regulation is get the design done. Because once you get the design done, I can go to his company and her company and your company, and I can start buying equipment. Okay, I can't buy it until I have a design done. Now, on the UAMP side, they're a municipal utility. They are subject to very, very different financing in the credit markets than Southern Company or Dominion or Constellation. I'm picking local utilities because you may be paying bills for them. Those are private companies. The municipals have different credit requirements. And I told you they're using 100% financing. And so policy tools like the loan guarantee program are very, very important. Very, very important to municipals. And they'll issue bonds. And I happen to have, if you know the organization, UAMPS, I had dinner with Doug Hunter, who's got this really, really sorted out. I mean, he has spent a lot of time thinking how he will structure the project financially. So the financial structure of a project is very, very important, okay? And how you handle, and here's the last thing, is the contract. So now you have risk. Here's how risk works. If Scott here is going to be buying for me, he wants me to take all the risk. That's what he wants. If I'm selling, I want him to share the risk, all right? So you can see the inherent conflict in here. One of the important things to do contractually is to de-risk these projects. What happens if I'm late? What happens if the stuff I buy doesn't get here on time? You know, you've got to take, it's enormously complex, okay? It's an enormously complex situation. You've got to break this down and you've got to look at the different parts of risk, how you can make risk palatable for private companies. If you're Russia Inc., it doesn't matter. If you're in China, it doesn't matter, right? There's no penalty per se, other than reputational, for spending more than you're supposed to. If you're an American company, you'll go bankrupt. Does that answer your question?
Yeah.
Other questions? Yes.
Councilor Jordan?
Thank you. My name is Sarah Jordan. I'm a professor here, assistant professor at SAIS. I have a very quick, twofold questions. The first being, back to the ERZ, the emergency response zones. I'm curious as to what drove the legislative changes, if it's primarily because of increased interest in SMR. And the second question is, I haven't heard of the SMR legislation before, so that's really interesting. So my question is it new? How new is it, and does it work? And can you see any effects? Because you did mention, you know, what quote unquote saved the industry so far, but that was clearly the existing plans due to market forces. So is there any, do you see there being any movement? Will it actually, do you see it working, and have you seen it start to work?
Okay, so I'll answer the second question first by saying I'll give you my cheat sheet on the legislation. You can look at all the different provisions in it, and it might give you some indication. And it's too early to tell. You know, it's too early to tell whether it's going to encourage, professor, or not, new build in those technologies, which you can have my cheat sheet. It's very, I think it's very interesting. What drove that is that came right out of Congress. I mean, there's a lot of interest in these smaller technologies from legislators from all over the country, whether it's from Tennessee or the state of Washington. I mean, people see the promise largely because of the economic development or the fact that they have companies in their states that are promulgating the different technologies. Okay. The first question, and because you're a professor, I'll correct you a little less gently. It's not. There aren't legislative changes. It's regulatory changes.
Thank you,
Okay?
yes, yeah.
So
You're
it's
correct,
it's
yeah.
really a regulatory change, and that what drove it is finally we have a chairman of the Nuclear Regulatory Commission, Christine Zwinicki, a nuclear engineer herself, and someone who's politically connected. She worked on Capitol Hill for a long time. She understands and has understood that you have to accept the inherent safety features in this new generations of technology, not just the SMRs that Annalisa was talking about, but the subsequent Generation 4 technologies, which have even lower core damage frequencies. You've got to look at this stuff and say, hey, wait a minute. If this has a valid empirical basis behind it, I don't have to license it the way I had to license Lipman's AP1000. You know, I can assume certain accidents are covered because they don't exist anymore. They simply do not exist. So, for example, in this SMR, you do not need, like you do for other designs, to ever look at the use of safety-related, of diesel generators to provide electricity during an accident, okay? Because there are no diesel generators. There is nothing safety-related, what they call 1E. There's nothing safety-related about the electricity. There is no AC power that's required for safe shutdown. Nothing. So, like in Fukushima, and it doesn't matter whether it was a tornado or a hurricane or a terrorist attack, when you lose power, you need electricity to shut down. You do not need electricity to shut down in these new designs. So we asked the regulators, you need to take that into consideration.
Yeah, so this is great. So it's not like saying the previous understanding of potential nuclear risk has changed. It's just that we're now enabling regulatory changes to open up for new technologies and innovations, which is great because you don't often see that, right?
That's correct. And one other thing, there's been a new development, and this is really boring, but I'm going to tell you about it. There's probabilistic risk assessment, okay? So rather than using what's known as a deterministic approach to accident analysis, you use a probabilistic approach, which means what's the probability of a certain event happening? Well, we have the tens of thousands of reactor years of operation that can now be essentially analyzed, and they do. And so you apply probability on these different events. Some are high probability, some are lower. Well, then you analyze the high probability situations and you spend less time on the lower probability situations. And so we see this in the operating fleet all the time. All the time. The situations are analyzed and they don't need to go before the regulator because statistically they have a ridiculously low level of risk. Okay? So it's using different analytical tools, which we didn't have. The people in the 1960s that developed the current fleet designs for reactor, they didn't have the computational methods, they didn't have the statistical packages or the software that could really analyze this stuff like we can now. So it's taking advantage of those things and not relying on past regulatory approach. That's a great question. Yes, sir.
Let me ask the last question. And you may or may not want to answer it, I'm not sure. We had, until recently, 4 reactors under construction, but now we have 2. There did seem to be a major advantage in the sites for all of them because they were in regulated states, which brought certain advantages. But 2 of them have been wiped out with cost overruns, as I understand it.
Yes.
And the other 2 that are going forward are still in some negotiations about who bears what cost. Is there anything in general you could say, what went wrong? Is it that contracting companies that were used by Westinghouse or whoever just turned out to be unreliable, or were not used to building such large projects? What are some of the factors that
Sure.
help explain that?
So it's a good question, and you're asking the right guy, obviously, so I'll, since I did all of those contracts, so
I won't quote them.
No, but here's what I would say. So there were 10 AP1000s put under contract, 4 of them in China, 6 in the United States, okay? Of those 6 in the United States, only 2, and those are the ones in Georgia, are continuing to be built. The ones that shut down, there were 2 in Florida and 2 in South Carolina. The 2 in Florida didn't go forward really and simply because of the 2008 financial crisis. Florida was sort of ground zero for the housing collapse in the United States. Load went away. I mean, something like 11,000 megawatts disappeared, as homes were abandoned and the resulting economic downturn that occurred. And it hasn't come back. And first it was Progress Energy Florida, which was then bought by Duke. They just said, we don't need the megawatts. Okay, so that's 2. But the 2 you're referring to are in South Carolina from SCANA. And there's a couple things. First of all, and not to be cute here, but to some degree size matters, okay? So SCANA is a very small utility. Those 2 projects represented almost the entirety of their balance sheet, number 1. Number 2, they were partnered with Santee Cooper. Santee Cooper is a municipal utility, okay? It serves the sort of the Charleston, the seacoast of South Carolina. So there are issues related to the sizes of those utilities, small utilities, that although they had a very favorable state regulatory environment, to your point, Will, the size of the companies made it hard to take on very much margin for error. Now let's talk about the error, okay? I think there were a couple things. First, the construction began before the design was fully complete, number 1. Number 2, Fukushima occurred. Fukushima resulted in a major change in the, if you visualize that picture of the AP1000, the air crash resistance had to be changed from concrete to reinforced concrete. That was a major, and that was sort of mandated by the Nuclear Regulatory Commission, and it was a delay of close to 2 years on the project. That was regulatory driven, all right, roughly, all right. What's the cost of a nuclear project? It is about, from my recollection, about 2/3 construction and about 1/3 equipment and project management and engineering. So now you've got 2-year delay in construction. That's a really sizable nut that has to be digested by companies that are in the field working, and there's a 2-year delay. It means designs have to change, analysis has to be done so that a new license can be issued. Second, to your point about the supply chain, and this is very important, we hadn't built a plant in the United States in 35 years, okay? And some of this is new stuff. So I pointed to modular construction. A module factory was built in Lake Charles, Louisiana, by Shaw. It's Shaw, Stone and Webster. They failed badly in trying to produce those structural modules. Those are the big ones that all the equipment goes into. Those structural modules are on the critical path schedule for completion of the reactor. You screw around with the critical path of any project, I don't care whether it's Heathrow Airport, Terminal 5, or the Olympics, or what it is, you mess with the critical path, you're immediately adding cost. All of those things occurred, and SCANA, the company in South Carolina, had a tough time digesting those costs. Now, my understanding is that they wanted to finish one of the two, because they felt it was very important for South Carolina to be there and finish. But the municipal partner, Santee Cooper, said, look, we just can't, we're pulling out of the project. Now, here's what's interesting. Dominion, headquartered in Virginia, in Richmond, is buying Scranton. And so included in that sale is that nuclear site. And I think it remains to be seen whether, in fact, at some point in the future, Dominion will finish up maybe one of those or not. But, you know, it's never one issue. It's a multiplicity of issues that line up and that cause project failure. Okay? So it's all of those things.
Thank you very much. Let me suggest we thank Dan once again for coming.